All right, so getting your notes out, talking about reaction rate. Reaction rate is, it kind of, the name sort of says what it does. It is simply, well, what is the rate or how quickly does a reaction happen? Or more specifically, what is the rate of the change of concentration of reactants or products? Which sounds kind of confusing perhaps, but think of it this way. You have A plus B, and that turns into C plus D. When they say concentration they'll represent with these brackets. Moles would be a measure of concentration. Moles typically per liter. They call molarity. That would be a measure of concentration. So when you're measuring the reaction rate, you'd be measuring how quickly do we turn A and B, do the concentrations of A and B go down, and do the concentrations of C and D go up? That would be the reaction rate. The faster that happens, the faster the reaction. Examples of a fast reaction, fireworks. Fireworks are just a chemical reaction. You know, I don't know if you ever really thought of it in those terms, but like that's really all you're doing in a firework. You're just doing a chemical reaction super, super fast, and the different elements involved in that are, you know, it's somewhat similar to the flame lab. Like it's kind of a similar principle. They give off all these colors as those electrons come down from the higher energy levels and release the light. A slow reaction would be like rust. Like the formation of rust is a chemical reaction, just like this would be here. But the rate that you make the product being rust here, just happens at a much slower rate than the rate that you see in fireworks. All right. So looking at things that would increase or decrease a reaction rate. Here's a good summary of all 5 of them. Temperature, catalyst, surface area, concentration, and then reactivity of the reactants. So we'll go through them one at a time. First one is temperature, which we've already talked about a little bit when I was going over like how you make sweet tea, like where they have to raise the temperature of the water. So, you know, because the higher the temperature something is, the faster the molecules that make up that reaction are moving around. The more things move around, the more they can collide. I'm going to underline this word collide because that's the key thing to really understand. We talked about collision theory. Molecules have to collide for a reaction to happen. So you raise the temperature, they collide more, therefore you will make more of those products. If you lower the temperature, molecules are moving slower, so the rate that you make the products is going to be down, is going to go down. Okay? And I think that makes a lot of common sense. Like that really isn't anything that should be blown anyone's minds right now. But, you know, I think it's just important to kind of have that at the front of your mind when you're thinking about chemistry. Okay, going to number 2, surface area. This one's a little less obvious, but think of it this way. If I were to, like, why don't, like, we have 8 lab desks, you know, around the room. Why don't I just push them all together and make one giant super lab table, and we all just sit around that? Like, really think about it. Like, legitimately, I don't have to have the room set up. I could just make one giant table, push them all together, and we all sit like that. Why would I not do that?
There'd be like unused desks in the middle.
Exactly, yeah. Good, Mars. Yeah, there's you reduce the surface area if you made one giant desk. I would not be able to fit everybody around that. Like, you don't have enough surface area. In a similar way, if you have, this would be your reactant. If your reactant is one giant blob, the space for these reactant molecules to access and break that down, think of almost like a sugar cube. Sugar cube's going to break down a lot slower than if you mash something up. This would be like me separating the desk out into smaller groups where this increases the surface area. Think of it, when you think of surface area, imagine you're painting it. If you were like in math class and you were to measure, you know, the surface area around that, you know, that rectangle versus the surface area around, you know, all of these, when you break the parts down, you would get a higher surface area. You need to use more paint to paint the outside when it's broken up versus when it's all in one clump. Now, what that has to do with chemical reactions is all it is molecules running into each other. That's all it is, right? Things running into each other. you are going to have more space for things to run into each other if you break them up into smaller pieces than if it's all one giant clunk. Okay? So that's all surface area is trying to say. Allows for more effective collisions. So that's a fancy way of saying it. All right, concentration. So very beginning of the notes I said concentration is the amount of something. Usually measure it in moles for every 1 liter. How many individual particles are there per liter? And this follows a lot of common sense, right? The stronger, the more you have of something, think of the hallways between classes. The more people there are in the classes, in the hallways, the more likely you are to like bump into someone. Not because you're trying to bump into them. There is just more people in the hallway, more likely you're going to like end up bumping into someone. Whereas if you have a lower concentration, fewer people in the hallways, if somebody bumped into your shoulder like right now when you're walking in the hallways, you would be offended. You'd be like, what is your problem? Like, you got a problem with me? Or like, get gear, like you paying attention to your phone. But if you're walking between classes, that would not be a crazy thing to happen at McLean High School, right? That'd just be like normal movement between classes. In chemistry speak, the more concentration, the more particles are going to collide. The more they collide, the more products you can then make. Okay, the faster the reaction happens. Any questions so far? Okay. All right, now number 4, this one's kind of interesting. And this one gets into our energy diagrams. The presence of a catalyst. Catalysts are going to speed up, they increase the rate of a chemical reaction. So think about our energy diagrams last class. So this is an energy diagram where we talked about the activation energy. That's the amount of energy you have to invest into a chemical reaction in order to make your products, which is represented by the bottom part of this curve to the far right. So if I want to make this chemical reaction happen, I have to add in this much energy. And the issue with that is, well, what if you don't have that amount of energy? What if you only have this amount of energy? Well, I had told you last class, like if you're trying to roll a ball up a hill and you only put in that much energy, then the ball is going to go back down and nothing happens. And that's an issue because when you think of like biology is basically just a bunch of chemical reactions organized into a cell. And then all these cells work together and make you. That's essentially biology. If temperature will raise the rate of chemical reactions, the issue is your body can't handle like 200-degree temperatures, but yet you still need to do chemical reactions at an efficient pace. So fortunately, we have things called catalysts in our body. What do we call catalysts? Anybody know? We're talking biology. What are catalysts in biology? You know? Starts with an E. Yeah. Enzymes, yeah. Enzymes are catalysts. Enzymes, what they do is they give us an alternate reaction pathway. They lower the activation energy. So instead of me having to put in, let's say this is 100 kilojoules of activation energy, now I only need to put in, let's say 25 kilojoules of activation energy. It's a lot easier to provide 25 than 100. Right? So the lower the activation energy, the more you can do that chemical reaction, and the faster you can do that chemical reaction. So that's how catalysts are going to increase the rate of a chemical reaction. If you don't have a catalyst, the reaction doesn't necessarily never happen. It just happens slower and not as often because it takes more time to save up that amount of energy to do the reaction. Now, last point on catalysts is they remain unchanged during a chemical reaction. That's really important when it comes to biology. Why would that be super important in biology? Why would you want an enzyme to be unchanged and reusable if you're thinking biology? Think of the opposite. If you had to make a new enzyme every time you want to do a chemical reaction, why would that be a problem? Think of clothes. Think of your shoes. Every time you wore your shoes, you had to buy a new pair of shoes. That would not be very convenient. That would not be very efficient. So catalysts, what makes them helpful is we don't have to keep remaking them. Because think about it. If a catalyst got destroyed after every chemical reaction, you would then need to do another chemical reaction to make the catalyst, And then that just kind of cancels out the chemical reaction that the catalyst does help. It's only because catalysts are unchanged and reusable that they actually help us do with these chemical reactions. So, anyways, last thing, well, a little more on catalysts. This is more just like a detail, like an example. So, here they're showing you, we have, this line here. This is no catalyst. This is with catalyst. The dashed line represents when you have the catalyst. So no catalyst, you got to put in 25 kilojoules of activation energy. If you do have the catalyst, it's only 10. Kind of like what we talked about. But what we haven't talked about is the potential energy, or you can think of this as the delta H of the reaction. Notice how it is the same whether you have a catalyst or you don't have a catalyst. Meaning the delta H here, the delta H is, this should be negative. The delta H is negative 15 kilojoules whether you have a catalyst or you don't have a catalyst. Meaning you end at the same spot in your products. Your products have the same potential energy, here 50 kilojoules, whether you chose to use the catalyst pathway or the non-catalyst pathway. The only difference when you use the catalyst is that you just have a lower activation energy. Yeah? When it comes to like applying this to the energy diagrams, this is a pretty important slide to understand. Any questions about it? Okay. All right, last factor is nature of the reactants. So if you think back to periodic table trends, one of them we talked about was the reactivity of elements. So, if you were a metal, we said that metals will increase in reactivity towards the bottom left, where francium is the most reactive metal. And then for non-metals, the trend is you go towards the top right, excusing the noble gases. That's why the noble gases are grayed out, because they buck that trend. Where fluorine is the most reactive non-metal. So in other words, if you want to make a chemical reaction happen fastest, you're like, I want to make some fireworks. Which elements are going to make the best fireworks? Well, you don't want to choose some of the most reactive metals and or some of the most reactive non-metals to react with. Okay? Or again, if you're going to predict how quickly a reaction happens without doing it, if you notice that the elements in that reaction tends towards the bottom left or top right, you know that that's going to be a pretty fast reaction. Okay. Okay. So there's a few different parts of the lab. Each one's kind of going over one of these different factors. One of them, you ever heard of elephant toothpaste? So I wish we could make the elephant toothpaste. We're not allowed to have you use hydrogen peroxide for elephant toothpaste, but we aren't allowed to order the pharmacy kind isn't strong enough to make it. You have to get a special higher concentration kind, and understandably they don't trust me to use that, which I can't blame them. So we just have to watch a video on it instead. This is this goes with getting that paper that you have in front of you. That would be the lab. That's going to be on page 2, so on the back of the first page, and it's this slide. It's this thing right here. So I'm going to play the video, and then this is what you're going to observe. They're going to show when they do elephant toothpaste, they're showing it with a catalyst. So, anyways, I'm going to play the video, and I want you to fill in the observation. Especially this observation when they do it with the catalyst. All right, let me get volume on.
.46 on this Saturday morning. Time to have a little bit of fun. Carl Nelson is here from the Imagination Station, and you brought some funky new glasses. Thank you. I'll put these on. Looking stylish. What are we doing today?
Probably hydrogen peroxide.
Okay.
You probably have this in the medicine cabinet at home, right?
Absolutely.
What do you do with it?
I'll put it in the cut.
Yeah.
Clean things off, right?
Doesn't really work that effectively for killing bacteria and cleaning out cuts.
Oh,
actually. Check out our Facebook page. I put a posting up there about how it doesn't work that well.
Yeah.
But one of the things it does do, here, I have a hunk of raw liver. If you could
Oh,
just
good.
go ahead and hold that.
Thanks,
Your
Carl.
body, as a part, I know, isn't it cool?
Yeah.
Your body, as a part of metabolism, actually generates hydrogen peroxide in its cells.
Okay.
And it's a very strong oxidizer. If you want to get rid of that hydrogen peroxide, there's something called catalase. It's an enzyme in your body that will break down the hydrogen peroxide into water and oxygen gas. So beef liver actually has catalase in it, and when you squirt the hydrogen peroxide on, just like on a cut, I assume you didn't want us to like cut you or anything to show how this works, right? It generates oxygen gas,
Okay.
And it looks really impressive, like it's doing something, but again, it's kind of a myth that it actually kills any sort of bacteria or cleans the wound out.
Oh, good to know.
But you can do something really cool with this. You can drop the lid.
Okay.
Now we're done with that.
Okay.
So what I brought with me is 35% hydrogen peroxide. This is 10 times stronger than what you have at home, hence the gloves and the glasses. You don't want to get this on your skin.
Okay.
And it gives off oxygen gas if you give it a catalyst, like catalase, or I brought a different catalyst with me. Now it's really cool because it can generate enormous amounts of oxygen gas. So we're going to trap that oxygen gas in some soap, okay?
Okay.
Do a nice little squirt of soap in yours, I'll do one in mine. And what we're going to do is simply pour a catalyst into this container of hydrogen peroxide. We'll break down the hydrogen peroxide into water and oxygen gas. Now since we have soap inside here, we're hoping for something
Is this gonna explode?
kind of dramatic. I don't know. And you know what? Go ahead and hold this.
Do I need to step back here?
No, no, stay right where you are, but let me do mine first.
Okay.
Let's do a little test here, see what mine looks like, and then you can try yours. So that's the technique, just dump it right in and see what happens.
Oh, wow, okay.
Okay, so
Whoa.
releasing
Okay.
lots and lots of oxygen gas, okay? So why don't you go ahead and do yours now. Yours is a little bit different container. It's got, just dump it in really quick.
Okay.
Perfect. Yours is like more like, and you just generate tons and tons of oxygen. It's being trapped by the soap.
Wow,
It's
okay.
like a supersized version of what kind of happens when you pour it on your body.
Sure.
Where that catalase enzyme breaks it down.
But again, we're not actually cleaning anything,
Well,
if you will.
Technically, the hydrogen peroxide, when it generates this oxygen, can kind of dislodge big hunks of stuff that
Okay.
might be in a wound.
Mhm.
But in terms of killing the bacteria, it's not really all that effective.
Sure,
But
okay.
it is. You can stick your hand over that, you can feel it. It's giving off some
Oh, some heat, yeah.
exothermic reaction. So it gives off a lot of heat when it breaks down, and it's just really cool.
So where would you see something like this concentrated?
If you want it to be a peroxide blonde, you could add some to your hair.
Okay.
That's where you get that term from. It's used for bleaching wood pulp to make white paper. It's a little bit more
Oh.
environmentally friendly than bleach.
Okay.
It's used in all sorts of industrial things like that. But as an interesting demonstration, it's also kind of cool.
All right, cool. So let me get the lights. So fill in this chart here. So this first one, this is when they poured it on the liver, more or less. Like this was like they used the weaker hydrogen peroxide. They had some of the catalase in that liver, but it wasn't quite as strong as like what you would see like when you added it, like when they used the higher concentration hydrogen peroxide. So think of it with like these aren't when they used it on the liver. How would you compare the observation there versus the second demonstration where it was the elephant toothpaste? What was kind of the obvious like difference there? All right. Okay. Foamy, sure. Yeah, more foam. No, I think that's actually a good way of putting it. 'Cause I think foam is the key thing you notice there. You made way more foam whenever there was that catalyst present versus, when there's no catalyst present, you had less foam being made. Okay. Now, this is, when I did this last year, a lot of people had a hard time, like they could do the observations, but this was a hard part of like people like explaining this. So collision theory, that's particles colliding. So why would it make sense according to collision theory that you would get more foam here and less foam here? So thinking back to the notes, like when we went over catalyst, why would having a catalyst allow us to make more of that foam? Nora, thank you. Boom. Yeah. Lower activation energy. EA is activation energy, and for the other one, it's higher activation energy. You know, that's good enough for me. But yeah, you know, if you want to like really explain it, the lower activation energy means you're going to meet the energy investment demand to make more and more of the product. What the product that we really needed to make in order to make that foam was trapping that oxygen gas. So having that catalyst present allowed us to make more and more of that oxygen gas. And again, we were able to do that because you had a lower activation energy with the catalyst. So anyways, this would be a similar kind of thing that I'd want you to do for like explaining all the other reactions. Okay, let me pause the video and then I'll explain what we do in the lab for the rest of them.